very much. Yeah, thank you. Thank you for staying for all 4 talks. Let me tell you, I really appreciate that. So, yeah, my name's Robert. I'm going to be talking about building a foundation for AI with ClickHouse and Apache Iceberg. A little bit about my background. Probably 2 things that are just kind of non-related to what I do today. I've been programming since the beginning of 1972, specifically sometime in January 1972. That was where our science teacher got a dial-up modem and a terminal that allowed us to connect to the local time-sharing service. And there was a pink book that said, "Welcome to the basic language." So that's how I got started, along with a couple other kids. And the other factoid is, I think the last time I was in this neighborhood was during the Cold War. So it's been a while. It's really great to be back. So let me talk a little bit about, why is this not advancing? Just 1 second here. Oh, that's weird, it didn't advance. Okay, so a little bit about the background of my company. My day job is actually running the company, but I've worked with databases for a long time. So Altinity is a vendor for ClickHouse. How many people have heard of ClickHouse? This is excellent. I think the closer we get to Eastern Europe, where it was written, the more people know about it. So it was written originally at Yandex, starting back in 2009, 2010. It was open sourced in 2016. Shortly after that, one of our founders, Alexander Zaitsev, applied it to an application that he was working on to analyze ads. And it was a great database, but really raw. So he started, with a couple other people, a consulting and education company, and that became Altinity. We now have close to 300 customers. We do enterprise support, so people run ClickHouse. We basically have contracts, and they can just ask us questions. We help them fix stuff when it's broken. We also have a cloud, so we run about half our business in terms of customers runs on the cloud, and it runs in a couple different ways. One is kind of like Redshift, where it's all up in our account. The other one is we can run it in your account. So as a result, we have a lot of background in ClickHouse, and we're really, really big on open source. That's kind of part of this talk series. Everything we do at the level of ClickHouse and all the ecosystem projects that we work on, things like Kubernetes operators, it's all pushed out into open source. So once again, we are not ClickHouse Incorporated. We fight like cats and dogs, but we do collaborate on this really wonderful piece of software, one of my favorite databases of all time. And here it is. I'm not even going to tell you what problem it solves yet. I'm just going to go straight into the weeds. So you've heard the phrase shared nothing. That's what ClickHouse is. Like all self-respecting databases or analytic databases of 15 or 20 years ago, it's a bunch of nodes. They all have locally attached storage. They're connected over a network. And when you add something to one of the servers, there's various mechanisms that allow the parts of the table to get replicated out to all the others. So it's a distributed system. We have something called Keeper, which is kind of derived from Zookeeper. It keeps consensus so we can track where the data is. And one of the things that's interesting about this is that, because we'll get to this in a bit, ClickHouse over time adapted to object storage in the sense that it could read files from object storage very well, like that is to say S3, and it could write them. But it doesn't really have the ability to store tables centrally on object storage the way something like Snowflake does. There's a proprietary version run by ClickHouse Incorporated that does it in their cloud, but the open source doesn't do it. We'll come back to that topic shortly. So what do people do with ClickHouse? Well, they solve problems in what we call real-time analytics. This is something like, for example, you are building a security management system, and you need to be monitoring logs to see if machines are violating, for example, rules that you have set. Hey, no DNS requests to known malware servers. That data gets fed in, often through an event stream, something like Kafka or Red Panda, and it comes to ClickHouse. That's over there, and merge tree is the name of the native table type. So that's the workhorse table. There are different engines. That's the most popular one. And what you do is this data gets loaded in, often millions of rows per second, very large volumes. The largest one that we deal with stores about 30 petabytes of data. And then it feeds all kinds of useful things for people who care about security, like real-time dashboards, like what's the state of the system. APIs, so that I can build custom applications that suck it out. and do things like alerting to say, hey, there's something that's happened that you should look at. So this is a very typical pattern that we use, and this is used in the securities industry, it is used for real-time marketing, it is used for things like observability, logs, traces, metrics, very, very common design pattern, and ClickHouse supports it very well. Let's have a look at how well. So this is a query that on a demo data set that is quite popular for databases. It's called OnTime. It's a US data set, and there's a line in it for every single commercial flight in the last 35 years or so. This is just looking, this is a typical query. It is looking for airlines that had, we know it won't include audio. Let's continue without audio. Okay, sorry about that. So anyway, so we're running this query, and we're just finding some carriers that you probably want to avoid because they constantly cancel flights. The key thing here is this comes back really fast. This was done on an Amazon VM, a pretty old one, an M5 that was with 8 vCPUs, so not very powerful, and it came back in 2/3 of a second. It had to scan something like close to 200 million rows. How did it do this? Well, there's 3 things that ClickHouse does really well, and we'll just walk through them. So if we had stored that data for this data set on MySQL is a row database, which means that in this query, if we touch any column in the row, we must read the whole row. There are 109 columns in this row, and so this is pretty big. In MySQL, you would have had to read 61 gigs with a single thread. So basically, this query would just go away and wouldn't come back. You might check back in a day and see if you got a result. Well, ClickHouse uses, like almost all analytic databases, it stores the data in columns. So we don't have a way of storing rows in the merge tree table. We have other engines that can do that. But in this case, we only read 3 columns. As a result, we knocked out over 98% of the data. So this is a huge speed up. We've gone from reading 61 gigs to just 937. But the second thing is, besides columnar storage, columns compress very well because they're the same type and they often have order to them. And in fact, the amount of data that we really read off disk was only 17 megabytes. That's tiny. That's a reduction of about 3,000 or 4,000 fold. So as a result, you go from not being able to do a table scan to being just able to do table scans casually to answer big questions. And what's even better, so you have columnar storage, you have compression, and then ClickHouse is just really, really good at using hardware. So when this query runs, it's going to run across 8 vCPUs, which are probably really 4 cores with hyper-threading, but they're going to be split 8 ways, and each of those on average will read 2 megs. That's why this thing is fast. And this is something that made ClickHouse incredibly popular, which did lead to a problem. And I'll get to that in a second. First, I want to talk about AI. So, like every other database on the planet, ClickHouse committers and the people who've invested in it are, of course, very interested in adding AI features. And one of the things that is happening is all databases are adapting to AI because it's a really, really important use case. And ClickHouse, there's a couple of key features in ClickHouse for those of you who are interested what it is doing, what we are doing for AI. One is vector search. How many people know what vector search is? Oh, that's pretty good. Okay, for those of you who don't know, basically AI represents information like words, phrases, entire documents using vectors. They basically reduce it to a vector which in some sense encapsulates the meaning of the entity that you're encoding. And vector search is a class of problem where you're looking, for example, you have a word like queen, and you want to look for similar words. So if they're represented by vectors, vector search might tell you that the word woman is closer than the word man to queen. So this is a very popular feature. Most databases are adding it. You have to have special indexing, and you have to be able to deal with very large arrays. The other feature that we're adding is MCP. So MCP is a model context protocol. It's a popular way of opening up different types of services so that large language models can get in and extract information. And so here's an example of how this might work. So this is an increasingly popular workload that people are trying to implement, where, for example, they're doing looking for derivatives based on something called the VIX, which is the fear index, which is a popular index that tracks volatility in futures. And so what you'll do is you'll give this prompt to Claude, and you'll say, hey, Claude, make me this report. Claude is configured so that it can talk to an MCP server. We have one. The ClickHouse Incorporated has one. And basically what this will do is it's basically a set of conventions and tools that allow Claude to go out and efficiently fish data out of ClickHouse without blowing up its context or without having to figure out how to do it. And then it generates a report. So this kind of works, and people are explaining, are trying it very, very actively, but the real impact is that's really significant is this is generating additional workload on the database, because these are new types of applications and people want to build a lot of these, and they often use the database in ways that are quite unpredictable. Moreover, AI has introduced another type of workload, which is training. And in that particular case, it's not just that you're accessing the database. What you want to do is get to the underlying source data, and you may want to get to it many, many times, because you're going to iterate across this and train or fine-tune models. So the effect of AI, like when you think about how do you adapt databases to AI, it's actually not just a matter of adding a few functional things like vector search or MCP servers. It's making the database support this workload. And that is actually a fundamental problem with analytic databases. And this was a problem that was already building for ClickHouse. That, I mentioned that we had a customer that runs about 30 petabytes. When I first started working at Altinity and on ClickHouse 7 years ago, we were seeing most workloads were in the range of a few terabytes at most. And so there's just this enormous increase in the size of data. And there's two kinds of problems that come up in these systems. The first is that this attached block storage gets really expensive as you get into the petabyte range. Not only is it more expensive to use this, particularly in the cloud, than object storage, you replicate it. So you have multiple copies of things that are more expensive. So this can cause the bill to be dominated by storage. The other thing is this shared nothing architecture leads to over-provisioning. Because the storage is fixed, it's difficult to raise the amount of CPU that's applied to it. You can do it, but it's kind of clumsy. So what people will do is they will just put more hardware than they need, because often these systems are built to handle emergencies. So for example, an observability system is really there to be used when something goes wrong. If the system collapses when you have a problem because a bunch of people are looking at the data, that's an issue, so you just over-provision. So this is a really key problem that existing workloads were kind of bringing this up, and things like AI have the potential to put even more load on it. So how do we solve this? Because this problem isn't solved well in open source ClickHouse. So the answer that we came up with, you've heard about Iceberg. We decided that we were going to try to implement shared storage, like what Snowflake does, where the tables, for example, the tables live in object storage, and then any number of processes can look at the same table. We decided, why not try to do this, but just use Iceberg. So and I'll just dig into Iceberg very briefly in a second, but Iceberg with Parquet, which is a very popular format for storing columnar data in files. And so we've talked a little bit about Iceberg. Here's just a reminder of what it is. Iceberg is what's called an open table format, and the way that it works is you have object storage, you have your data stored in files, typically Parquet. That's that's the most popular format. Parquet is just a way of storing columnar data with very, very good rate of compression and a bunch of metadata that's baked into it. You then have metadata from Iceberg that remembers which files belong to which tables at which times. And then finally you have a catalog, so that you don't have to scan a bunch of metadata files. You can go to the catalog and essentially say, hey, for table X, where are the metadata files? Just point me to them, so I don't have to find them myself. And this then allows any application that knows the APIs to read the catalog and can process the metadata, can go read this data. So the final thing that this does, in addition to storing a bunch of data cheaply, is allows people to share it, because there's a lot of libraries that understand this format. So that's Iceberg. So we started a project a couple of years ago. It's called Project Antalya, and it's our way of adapting ClickHouse so that it can use Iceberg as primary storage. Now, ClickHouse is a huge project. It has commits from hundreds of people each year. And the upstream ClickHouse is very actively working on data lakes, but it's more focused on integration, like reading and writing from data lakes, and talking to different types of vendor catalogs. We're looking at using Iceberg as primary storage, so we have a slightly different set of considerations, which are listed here. Just one example, we are implementing separation of storage and compute in ClickHouse, which didn't really exist prior to us starting this project, because it was using the shared nothing model with attached storage. There's a bunch of other issues, but basically these things kind of complement each other. And in a way, even though, as I said, we compete with upstream ClickHouse or with the ClickHouse Incorporated, these things do fit together, and people get the benefits of both of them. So just at a code level, to follow up on that, there's the upstream ClickHouse repo with about 40,000 or 45,000 stars on GitHub. We're basically downstream, so we basically operate as a branch. We have commits going into our repo. Whenever something is consistent, sort of useful in upstream, we push it up because we don't really want the things to vary too much. And then we do our own builds, so which you can get at those addresses. So what do we do? Just specifically, separation of storage and compute. We built these things called swarms. So we basically extended ClickHouse. You have the normal ClickHouse clusters, because a big thing about building this is don't break the stuff that already works. It's great. So you can take an existing ClickHouse cluster and you can just drop in these swarm clusters, which are basically just a bunch of stateless ClickHouse servers. And what you do is you can take your queries, and if they're going to go to a data lake, you just add that little property, what's called a setting, and just give the name of the swarm cluster. And then what we'll do is when we're doing our planning and query, we'll just delegate all the reads to Iceberg out to the swarm cluster. And so we have, there's a bunch of details here. We have a lot of caching. We have some tricks where when we're doing the delegation, we try to recognize when we've read a particular file on each swarm node, so that we use those caches efficiently. So that basically gives us separation of storage and compute. It's been around for about a year and works pretty well. Now, as we start to think about putting these things together and getting full value, what we kind of want to do is combine the storage. Because it turns out that if you look at the native merge tree storage and Iceberg, they're kind of complementary. And they might fit together because merge tree, and I'll show you proof of this in a second, it responds almost instantly. It's a very, very low latency. It has built-in compaction, things that data lake formats like Iceberg don't do. On the other hand, Iceberg is cheaper. You can scale the compute. Moreover, you have virtually unlimited I/O bandwidth. This is a big problem in storage. You can only read single disks at a certain speed. But the nice thing about object storage is many processes from around the net can be looking at the same object storage and reading it. So you can get enormous scaling, and it's shareable. So these things could be, seem like good complements, which taken together would give a very powerful whole, but the question is, will it work? And in databases, the first thing we mean when we say will it work is, what's the performance like? Because normally new things, it kind of sucks. So what I'm going to show you is just a lot of details here, but the key thing is this is some anonymized data from one of our customers, where we compared a real workload of 40 of the most common queries and just kind of check the performance of merge tree versus the Iceberg access. Oops, and we found some interesting things. So merge tree is, as I mentioned, has very, very low latency. And so what we did in some of the queries, merge tree, which is that little red guy there, these come back all in about a tenth of a second. So there's a lot of queries for which ClickHouse, once the data is loaded and the yellow is a cold run, the red is a hot run, it's extremely fast. So if you have things where you just need a result back, like so that you can show something in the time you're rendering a page, for example, merge tree is really great. So it's a real winner on hot data. And so that answers the question, hey, is merge tree going to be good for the low latency stuff? Well, on this real workload, it looks pretty good. And there are cases where it does take longer to load because it takes longer to read off the block storage that we're using in Amazon. But in every case, the Iceberg data is slower. And that's partly because it's distributed. We have to spread it across a bunch of processes. There's a number of hops, so those queries tend to be slower. On the flip side, as the data sizes increase, and we're scanning very, very large amounts of data, as we look at this, in this set of queries, in every single case, Iceberg was way faster, often by a factor of 10. So ClickHouse is very slow to load the data, and even when it had the data fully loaded, it was still, when it was running hot, it was still very slow. Part of the reason is because the caches can't hold the data, so it keeps coming back and reading it again. So from a performance perspective, what these data show is that we did get the expected results. Merge tree very, very good on the hot data. Iceberg pretty quick, even on hot data, but very, very good, very, very effective for the cold data. So that allowed us to do the next step, which is we got separation of storage compute, confirmed performance. Now what we're doing is we're combining these two table types so that what you can do is take existing systems which are hitting the limit for storage, and we can put something across the top of them called a hybrid table engine, and this is a new engine for tables in ClickHouse that applications connect to this. It looks just like the regular merge tree engine, but underneath it implements what we call tiered storage. This is something ClickHouse implemented a long time ago in the merge tree engine itself. The hybrid table engine allows us to have tiered storage going across completely different table types. So you can have a merge tree hot tier, and that's where you get fast ingest that's instantly compacted so that it turns into nice big files with low latency, and then it gets transferred out to the cold tier, which is scalable and cheap. The transfer part is something we're still working on. Right now you have to use Python to move the data, but this will eventually be built into ClickHouse so that it's just a function of the database. So how do we actually do that? Oops. Okay, there's a key thing here that when you do tiered storage, and this is kind of an interesting computer science problem, you need to decide what's the boundary between the hot tier and the cold tier. We use what we call a watermark. It turns out in most of these data sets, they're time ordered. So you can just use, like if there's an event date or something like that, that could be your divider. And so what you'll do is you'll move forward like a day at a time, for example, and as the watermark, when you get ready to move the watermark, you just move the next day's data over, push it into Iceberg, and then change the watermark. What does that actually look like? This is code. And one thing about ClickHouse that's really, really cool is it's just a tool set. It's, it's kind of like a high performance race car. And it has a bunch of tools in it that allow you to build interesting applications. And so this is a typical example that this looks kind of complicated, but what it's basically doing is the hybrid table gives us two types of storage. There's this first one that points to the hot data, and it has this, and it basically has a predicate that says, which data go in this, we call this a segment, which data go in this segment, and then there's another segment which is the Iceberg data, and then another predicate to say which goes in that. And so basically what this is doing is this is a piece of code that we can write that splits the data in this table into hot and cold with a watermark between them. So this means that you can have all kinds of different ways of splitting the data up. We're just taking the simplest one. So the end goal on this, and this is to come back on these big workloads, is to basically not just support a bunch of data and do so cheaply and allow AI, but actually to allow people to build a single unified pipeline that multiple apps can access. Because the whole point is to try and keep these systems are big, the simpler we can make them, and the more we can allow people to share a single chunk of data for all applications, the better these systems are and the easier they are to run. So that's basically where we're headed. And along the way, this is just a couple final points. So we've learned some interesting things. These, as you get into these adventures. So specifically around this storage architecture to allow low-cost, scalable storage. So we've proven that these complementary storage types do fit pretty well together. This looks like it's going to be a good combination. The problem is really hard because we're extending systems that exist and we don't want to change ClickHouse. It's just making these two table types be transparent to applications, because the really key thing for introducing an innovation like this is to not to have to change application code. So we're close on that, but there's still a few changes you have to make, but this is a solvable problem. Another thing, it all has to happen in SQL, so people just need to be able to do a few, sort of basically define schema and have it work. Another thing that's really important in this process is we have learned over the last few years that people really want to do this in their own environments. The system that I'm showing you does exist, similar systems exist in cloud services that you can connect to, but your data lives there. Most people really don't want that, particularly if they have large data sets. And so as a result, this design that we have works anywhere. It'll work in high-performance computing clusters. It will work in Kubernetes. Wherever you want to run it, it will still work. And then finally, automation is really crucial. I think a big issue with Iceberg is it's very powerful, but it also has a lot of little pieces. And so having that automated and just so it runs by itself is really key to success. And the final thing is, coming back to the topic of AI, AI is really new technology, and I think many of us are kind of struggling. There's no question it's going to be transformative. It already is in many ways, but actually using it effectively is not quite as easy as just, coding something up and shipping it. Here are two things that we're seeing as we go along that seem to work. So the first one is agentic coding. How many people use Claude Code or Codex? Yeah, do you like it? So last year, basically last year was a really big year for this because it started on January 1st, 2025. You ask people, is this going to work? And a lot of people just say it sucks. It's never going to replace programmers. By the end of the year, you have people like Armin Ronacher, who has worked at Sentry, or Mitchell Hashimoto, who wrote Terraform, and they're saying, hey, this is transformative. This is real, and this is a new way of building code. This is clearly going to work. And where we see this is clearly going to affect how people build real-time analytic applications. So one of the things that every time we're engaging with developers, it's a really good chance they're using Claude Code. So we need to build open source projects that make this easier to do. For example, by having agents.md or having patterns for applications that are easy to, where you can tell Claude, hey, look, go look at this pattern, look at my data, make me one like that. This is for real, and it's something that really works. The other thing, and this is very specific to our specific industry, is using agents to analyze database performance or fix problems also looks like a winner. And there's a reason and so basically, if you have MCP that gives your model access, if you have access, and you have monitoring data available that the LLM can find, and if it can see the database schema, it's surprisingly good at finding problems. So we've seen this. We haven't released anything for this, but we can see this working. There's something that unifies these two things. I don't know if anybody notices this, why these two seem to work, because there's other things that don't work. Both of these problems happen to be things that are not very deeply affected by hallucinations. So this one right here, the agentic development, the reason it's safe from hallucinations is you typically, if you're using it right, you have the developer paired with something like Claude Code and watching it and correcting the hallucinations. This one here, we don't let it write to the database. So we let it give us results, but we actually don't let it go make changes. And so if there's a hallucination, hopefully we'll notice and correct it. So anyway, these are not directly related to everything, but these are things that we can see that look like they work. I'd be interested to hear what you guys are doing that works. You can try our stuff now, but that's the end. So thank you very much. You can get the slides here and connect with me on LinkedIn.
Some questions?
Yeah, I've noticed some similarities between this architecture and Redshift and Redshift Spectrum. Are there or is
which is similarities between this and?
The Iceberg table and the merge tree table?
Yes, yes, that is right. And let me go back because actually there was a key point. So one of the reasons that we thought this was plausible to use these together is the designs are very similar. So you have big tables. They are divided into parts. So there's a partitioning spec. In Iceberg, we call partitioning by and ClickHouse. Both of them have a notion of order. So that's built into. They have similar data types, except that, God knows, they don't have an unsigned type in Iceberg. So there's variations like that, and then finally, so there are these basic similarities, which mean that we probably can get it to work, but the devil is in the details. And I'll give you an example of one just sort of horrible problem that has come up. Have people dealt with time zones in these large data sets before?
Yeah.
I just talk about a fucked up mess. So we've hit problems where because Iceberg and merge tree have different ways of dealing with time zones. We get cases where Iceberg will effectively partition it differently because it thinks it's working with a different time zone. And these are things like just have you pulling your hair out. So yes, there's basic similarities, but then you get problems like this. And so the trick is to figure out what are the conventions that you have to follow to make sure that the data, which, for example, comes into ClickHouse, will end up being properly formatted so that it'll still be commensurate with the merge tree.
But there are similarities with Redshift,
yes, big
Spectrum, right?
Big similarities, yes. Well, see, I think most analytic systems are organized the same way. It happens that merge tree and Iceberg actually are pretty similar in their table types. Others are differ more widely. Thanks. That was a really long answer to a short question.
You mentioned that special way which ClickHouse handles time zones.
Yes.
Recently I found out that if you dump table with a date column, it converts to integer field, and no any other system understands that.
Yeah.
So ClickHouse has its unique way. But my question was about Iceberg support in kind of vanilla ClickHouse.
Mm-hmm.
If I remember correctly, right now they recommend to use functions for read-only access. And Iceberg engine is alpha or beta state. And as I understood, you made huge progress and you made it work better, right?
That's correct. But we also did we also were able to, because we were solving a specific problem, So for example, this tiered storage, one of the things that we can do is we can use different mechanisms to write to Iceberg. So vanilla ClickHouse has very limited support for writing to Iceberg. What we do though with tiered storage, typically you're going to move the data to Iceberg at intervals, like a day or 2 days or 3 days or something like that. So we can what we did was we wrote additional tools that allow us to export parts out to Parquet and then load them in. And we do this as a bulk operation. And this means that we don't have to deal with a bunch of very complicated things like, for example, compaction of data or metadata explosions, which will happen if you write to Iceberg too often. So we kind of solve the problem by not having it, by only doing bulk transfer, if that makes sense. That's what really allowed us to extend ClickHouse behavior without having to do some stuff that's actually quite hard to do.
ClickHouse has storage policies which can be useful for using shared access between merge tree and Iceberg. Do you want to implement some simpler syntax?
We actually were one of the teams that worked on that stuff. We worked quite a bit on tiered storage. So ClickHouse has had it for a long time, and so yeah, ClickHouse, for those of you who use ClickHouse, you may know about TTLs, for example, or TTL moves. This is a very powerful feature. That's exactly where we're headed. We want to implement that, but it's so that it's purely in SQL. And you'll set a policy on your table, and then it'll just move to Iceberg. But it's going to take a little while to get there. But that's our Jerusalem, if you will.
And you showed tests, ClickHouse on merge tree, ClickHouse on Iceberg.
Yes.
But did you try, for example, Spark on Iceberg versus ClickHouse on Iceberg?
No, we have not. We have not done that comparison. Generally speaking, our customers do it for us, and they all complain about it. So, really, that's like a big ask is to try. And one of the opportunities is ClickHouse is very, very fast, and our hope is to be able to apply it to some of the applications that people are now using Spark for. And I think the upstream folks feel exactly the same way. They want to liberate the data from Spark.
Thank you.
You're welcome. Thank you.
We're also very interested in that agentic architectures where you've got two patterns of using Claude Code for coding, or you use your analytic database with MCP. But we're considering like combining these things. So you have Claude Code, and you don't use MCP. You just give it like DuckDB clang, or you
Right.
give it. And then you give it the context as a bunch of files. So now it's running on
Right.
a file system.
Right.
And then you ask your analytic profiles. I just wonder if you've seen that pattern in your travels.
No, but what's interesting to me about LLMs is that all of these patterns, it's almost like any of these patterns is just sort of, pretend you had a human that you wanted to do this work. You would just write them a little description of how to do it, and one might be, hey, use DuckDB. One might be, hey, there's a tool that you can, like MCP. I think the key thing about MCP that, and again, don't hold me to this. If you give somebody a tool like DuckDB, I think the big problem you run into is it gets really hard to support things like single sign-on. So this is actually one of the hard problems that we see in access to data. You want to have, like if you're in some big company and you have this big data lake, you actually want to be able to implement security on the database so that somebody who's using the LLM to solve a problem can't see stuff that they're not allowed to see. And there's two parts to that. One is by accessing it through the database will give you a security model, a very powerful one, with role-based access control, where the roles and the privileges can be defined in SQL. So that's something that's really important. And any database tool that points to the database will get a benefit from that. For example, in ClickHouse. The second is to make sure the database shares the same notion of security as the rest of your organization. So what you basically want to do is connect ClickHouse to something integrated with OAuth, and that's actually a big feature addition to ClickHouse that we did, so that becomes possible. It didn't totally answer your question, but I think those are sort of the issues that people are grappling with to try to make this stuff work. I hope it helped.
Hi, I have two questions, and they refer to this hybrid compute engine you were talking about. So my first question is, you were talking that basically this movement from the hot from the cold storage to the hot, from the hot to the cold storage is based on these watermarks. So how do I define the size of these watermarks? Do you have there any?
Basically, the notion we had, so once again, I said that the watermarks are based on something in your data. Because the interesting thing is you can't, you have to have some way of deciding when it is time to, which data belongs to, to which segment. And so I think this is going to turn, ClickHouse has a lot of experience with tiered data already, because this feature was put in years ago, I think at least 5, and it's very widely used. So usually the notion is you think about this when when you build systems, the way that it works right now is you put a policy on the table and you say, hey, at 30 days, move the data to cold storage. So it's going to work the same way. What we really want to do with what we're trying to do here with Iceberg is just free this stuff from being in block storage and just have it be in shared storage. But the ideas behind it are the same. So it will be based on something that you can read out of the data, like time. And then there's some details to that, but that's the basic idea. And I think if we could just imitate what ClickHouse already does for the merge tree tables and do it across to Iceberg, I think that would solve the needs of a lot of people, at least most of our customers. Does that answer the question?
Kind of, yeah, because my understanding of these watermarks are that this notion is usually used in the domain of stream processing, like in Flink or in Kafka streams. Yeah. So it kind of makes sense that when you're ingesting data from Kafka streams, you have there also kind of your windows, and usually this watermarks is defined by the size of your windows that you're having there.
No, this is a different,
if this is something else.
It's a very different notion. And here's the thing. So when this data is coming in, you want this stuff in real-time systems. And I guess a point that I probably didn't stress strongly enough, I believe, and we believe as a company, that actually combining these storages, these types of storage is very powerful for these systems. And the reason is, when your data is coming in, you're reading in data in many of these systems, millions of rows per second. You actually want it to sit here for a while. So your window is very big, because what you want to do is give this time to compact so that you have very, very large files. These files could be like 50 gigs in size. And by files I mean the parts of the table. So you can think of like the window, if you will, is kind of logical, but it's on the order of a week or something like that. So let these guys compact and then move them in a big bulk move operation. So it's not the same as like a window that you would have in Flink. But those are relatively short durations, and they do have, and they're related to like, hey, how much can you hold in memory before you have to let things get overwritten? If that makes sense. This is solving a different problem. We really want to allow this stuff to compact fully. So, and the fact is that people also are looking for, this has better low latency performance than Iceberg does. So again, it's like, how long are you willing to pay for the low latency performance? That determines the length of this window. Did that answer your question?
Yes, thank you. And my second question about that is also kind of what you started talking about previously, is the use of memory, and when do you spill to disk from memory?
That's a great question. We really try to avoid ever spilling to disk. So what we would rather do is it's incredibly expensive to do it, because once you start writing to storage, it just gets really complicated. So in general, so ClickHouse, for example, in general, even without leaving aside Iceberg or anything like that, it can spill to disk. It's rarely used. What we usually do is just get a bigger machine with more memory. And in fact, the idea behind the Yeah, let me go to the, so here's the swarm. The idea here is the place you're, in these things, if this is the hot data, this is a relatively small subset. You probably don't need to spill the disk for these queries. It's this big one that you have to, you know, the long tail of data where you're gonna have to spill the disk when you do large aggregates. So what we do here is by using these swarms, we can actually, if we know some big job is coming along that's gonna scan a bunch of data, you can scale the swarm up. So what you're doing is you solve the disk problem, the spill the disk problem, by allocating a bunch of RAM temporarily, running the query, and then dropping it again. That's why these swarms, these scalable swarms are really important to solve this problem. We just try and allocate more memory. Does that make sense?
All right, yeah, thank you. I have also a couple of more questions. Maybe we can.
Sure,
do this
gladly.
offline.
Yeah, I'd be delighted.
I think we finish here. We had a lot of questions.